You know, when most of us picture the solar system, we think of this incredibly stable, predictable thing. Planets orbiting the sun like perfect gears in a cosmic clockwork. You could just wind it up, calculate everything, and know exactly where things will be millions or even billions of years from now.
Right. That's definitely the classical view, yeah. Almost Newtonian.
Oh, yeah.
It's a comforting image. Order in the cosmos.
But what if that picture is fundamentally, well, incomplete? What if our cosmic neighborhood is actually kind of chaotic? Less of a perfect clock and more of a, I don't know, a delicately balanced, slightly tipsy mobile.
That's exactly where the cutting-edge research takes us. The more we understand the intricate gravitational dance, of the planets and how our solar system interacts with the rest of the galaxy, the more we see these, well, surprising layers of unpredictability.
Absolutely. So for this deep dive, we're going to unpack some recent scientific findings that really challenge that old, simple clockwork image. We're looking at the forces within the solar system. The planets pulling on each other and the sources from outside, like stars just passing by.
And to do this, we've gathered up a stack of sources for you. We've got core scientific papers detailing these complex simulations, articles that break down these sometimes mind-bending results for the rest of us, and even some of the back and forth happening online among researchers and science communicators.
Our mission today is basically to pull out the most important insights from all this material. What are scientists actually learning about the solar system's long-term fate? What could potentially destabilize things? And maybe, why does this fascinating peek into the universe's mechanics actually matter to you right here on Earth?
Let's dive in.
Okay. So you mentioned the classical view, rooted in Newton. The idea was pretty simple. Gravity works in a predictable way.
Right.
If you know the mass and position of everything at one moment, you can just project forward or backward indefinitely. It's all deterministic.
Exactly. And I mean, for a system with just two bodies, say, the sun and Earth that works beautifully, you can write down the equations, solve them, predict their future orbits with incredible accuracy.
Okay, but we have more than two bodies. We have, well, 8 main planets plus dwarf planets, moons, asteroids, comets, loads of stuff.
Exactly. And that's where things get profoundly more complicated. The moment you introduce a third body or a fourth or, many more, the gravitational interactions become incredibly complex. This is what's known as the N-body problem.
The N-body problem.
Slam.
And this is where that idea of chaos starts creeping in.
Precisely. Brilliant mathematicians like Henri Poincaré, back in the late 19th, early 20th centuries, they realized that for 3 or more bodies, the equations describing their gravitational dance just don't have a simple general analytical solution. Not one that holds for all time.
Meaning
small, even imperceptible differences in the starting positions or velocities can compound over vast timescales. They can lead to vastly different outcomes.
So it's not like random chaos, total disorder, but more like extreme sensitivity. A tiny flap of a butterfly's wings today could mean a hurricane somewhere else years later, that kind of thing.
That's a classic analogy for deterministic chaos, yes. For the solar system, it means while we can predict planetary positions with really high accuracy for centuries, maybe even millennia, pushing those predictions out over millions or billions of years runs into fundamental limits. It's because of these complex nonlinear interactions. The long-term future, while it's governed by physical laws, becomes inherently unpredictable in its precise configuration.
Wow. And it turns out our own solar system might be less stable from within than we thought, precisely because of this N-body complexity.
That's perhaps the most surprising internal finding from recent simulations, yeah. While the solar system has been remarkably stable for, 4.5 billion years?
Right.
The modeling suggests this stability isn't guaranteed forever.
Okay, so what's the weak link then? Which planet is the potential wild card?
Surprisingly, it's the smallest one, Mercury.
Mercury? Really?
Yep. Simulations show there's a non-zero chance, it's estimated around 1%, that Mercury's orbit could become highly unstable within the next, say, 5 billion years. Before the sun becomes a red giant.
Like 1% chance of Mercury's orbit becoming unstable. Okay, 1% sounds small, but 1 in 100 over billions of years. That's significant in cosmic terms, isn't it?
It is.
And what happens if Mercury goes haywire? What does that look like?
That's where the simulations get pretty dramatic. If Mercury's eccentricity, how stretched out its elliptical orbit is, gets significantly increased. Maybe it enters something called a secular resonance with Jupiter.
Whoa, hang on. Secular resonance. Could you quickly break that down? What does that mean?
Okay, yeah. So think of resonance just as a kind of rhythmic synchronization, right?
Okay.
A secular resonance isn't about the planets meeting up at the same spot regularly. It's more about how their gravitational pulls affect the shape and the orientation of their orbits over really, really long periods. So in this case, a secular resonance with Jupiter could mean Jupiter's immense gravity, acting over eons, subtly but consistently pulls on Mercury's orbit in just the right way to make it more and more stretched out. It's like a gentle, persistent nudge that just accumulates over time.
Got it. A persistent nudge that stretches Mercury's orbit way out.
Mm.
And the consequence of that.
Well, if that happens, Mercury's orbit could become so elongated that it starts crossing the paths of other inner planets, particularly Venus and Earth.
Oh.
The simulations show potential outcomes ranging from Mercury colliding directly with the Sun or Venus,
Okay, that's bad for Mercury.
to Mercury's chaotic movement, triggering a kind of cascade of instability among the other rocky planets.
A cascade? Like dominoes.
Sort of. This could potentially cause Venus or Mars to collide with Earth, or even Earth itself to get ejected from the solar system entirely, or maybe plunge into the Sun.
Wow. Okay, so the key insight here is how a tiny planet like Mercury holds this surprisingly large, albeit low probability long-term risk for the entire inner solar system setup. It's definitely far from that perfectly predictable clockwork we started with.
It really is. And what's perhaps even more fascinating, maybe, is that this isn't purely theoretical modeling. We've actually found real-world geological evidence that seems consistent with these kinds of chaotic orbital shifts happening in the past.
Geological evidence, you mean from rocks here on Earth?
Exactly. There are studies of ancient sedimentary rock layers in France, layers laid down between about 113 and 123 million years ago.
Okay.
And they show patterns in how they were deposited that seem to correlate with astronomical models. These patterns align with predictions of transitions in those resonant terms. We mentioned the complex gravitational rhythms.
Right, the secular one.
Yes, related to the orbits of Mercury and Jupiter. The models predict a kind of shift around 117 million years ago, and the rocks seem to have actually recorded the consequences of that orbital change.
So wait, the rocks on Earth are like a fossil record of past orbital chaos that the math predicted. That provides incredible validation, doesn't it? That these subtle gravitational interactions do have measurable effects over geological time.
It certainly strengthens the case, yeah. It suggests these predicted long-term instabilities aren't just, theoretical possibilities, but are based on real physical processes that have likely occurred in the past.
Okay, let's shift our gaze outward then, past the rocky planets, towards the outer solar system. Specifically, let's talk about Pluto.
Ah, yes, Pluto, the famous dwarf planet whose orbit is, well, it's pretty eccentric, isn't it?
Yeah, highly inclined relative to the other planets' orbits, and it actually dips inside Neptune's path sometimes.
It does.
Which seems really counterintuitive. If it crosses Neptune's path, why hasn't it, collided with or been ejected by Neptune ages ago?
That's the fascinating puzzle of Pluto's orbit. Despite its unusual path, it's locked in this really delicate gravitational dance that has kept it surprisingly stable for billions of years. Even though simulations show its orbit is, and this is a quote, surprisingly close to a zone of strong chaos.
So it's stable, but, barely. Precariously.
Precisely. Its stability relies heavily on the giant planets, particularly Neptune, through a mechanism called the 3.2 orbital resonance.
Okay, another resonance, a 3.2 this time, like a cosmic rhythm again.
Yes, but a different kind than the secular one we talked about with Mercury. This is a mean motion resonance.
Okay.
It means for every 3 times Neptune completes its orbit around the Sun, Pluto completes exactly 2 orbits. This synchronized rhythm ensures that whenever Pluto is at its closest point to the Sun, and technically inside Neptune's average orbit, Neptune is always somewhere else, far away on the other side of the Sun. They basically never get close enough for a dangerous gravitational interaction.
Okay, so Neptune keeps it safe through this orbital dance. What about the other giant planets? Do they play a role?
They do, and it gets more complex. Ironically, Uranus actually seems to have a destabilizing influence on Pluto's orbit over timescales of tens or hundreds of millions of years.
Really? Uranus makes it worse.
It seems so. If it were just Pluto, Neptune, and Uranus, Pluto's orbit likely wouldn't be stable for the whole age of the solar system.
So if Uranus is trying to mess things up, what saves Pluto?
The big players. Jupiter and, to a lesser extent, Saturn.
Even though they're much farther away.
Exactly. Despite being much farther away from Pluto than Neptune or Uranus, their sheer mass exerts this powerful, stabilizing gravitational influence. Jupiter, in particular, provides a crucial stabilizing force that counteracts Uranus's destabilizing tug, and that ensures Pluto's orbit remains stable for at least 5 billion years in the simulations.
Huh. It's like Jupiter is the ultimate gravitational anchor for the whole system, keeping things from spinning off into chaos, even for a distant little dwarf planet like Pluto.
It plays a critical role, absolutely. But even with that stabilization, the fact that Pluto's orbit is still described as surprisingly close to a zone of strong chaos just underscores how finely tuned this whole balance really is.
Yeah.
It's a great example of how these complex multi-body interactions create both stability and, well, the potential for instability right here in our own solar system.
Okay. So we've talked about the chaos that can arise from the planets themselves interacting, but that picture of the solar system as this isolated bubble, that's also not quite right, is it?
No, not at all.
We're part of a much bigger system, the Milky Way galaxy.
Absolutely. The sun orbits within the galaxy, just like billions of other stars, and those stars aren't stationary relative to each other. They're all moving, which means, inevitably, stars fly past our solar system constantly, really, on cosmic timescales.
Okay, but space is huge. Aren't most of those flybys way too far away to actually matter?
Most are, thankfully. A star passing a few light years away isn't going to noticeably shift Earth's orbit, no. But think about it statistically. Over the 4.5 billion year history of our solar system, hundreds of thousands of stars have likely passed relatively close, maybe within, say, a few thousand AU astronomical units.
A few thousand AU. That's still like thousands of times farther than Earth is from the sun. Pretty far.
It is far, yes. But their cumulative gravitational tugs aren't necessarily zero over cosmic time. And recent research is really starting to quantify the long-term effect of these external gravitational nudges on solar system stability.
Okay.
The core idea is that while any single distant encounter might be negligible, enough of them might add up, or maybe a single closer one could have a lasting impact.
Right. And these passing stars don't just potentially affect the future. They can add uncertainty to our understanding of the past, too. Is that right?
Exactly. When scientists run simulations trying to trace Earth's orbit back millions of years, accounting for the potential influence of passing stars actually introduces more uncertainty into those historical predictions. It effectively reduces the reliable time frame for tracing Earth's orbit backward by something like 10%.
So even though we weren't here to see them, those past stellar encounters actually complicate our ability to know precisely where Earth was in its orbit eons ago.
Right. And researchers have even tried to simulate the potential effects of a specific star. There's a sun-like star known as AG 7977, which might have passed somewhat near our solar system roughly 2.8 million years ago.
Was that pass thought to be significant? Did it do anything?
Well, the simulations explored its potential impact, and what they found was that the simulated changes to Earth's orbit after such an encounter were actually consistent with some geological records from around that period.
Consistent how?
For instance, they showed orbital variations that kind of align with patterns seen in geological evidence related to past climate events, like variations seen around the time of the Paleocene, Eocene thermal maximum, the PTM.
Wait, hang on. Are we saying this star pass caused a major climate event like the PTM?
No, that's a crucial point, and the researchers in the source material are very careful to clarify this.
Well,
their simulation shows consistency between a potential stellar influence and geological records. It demonstrates the potential impact of such an event. But they are not claiming that HD 7977 itself triggered the PTM. Their models simplified some factors that are important for precise past orbital calculations.
Got it. Okay, so it's not a definitive cause and effect, but it shows that stellar passes can, in principle, influence orbits in ways that might leave a detectable fingerprint over geological time. That seems to be the key takeaway there.
Exactly.
External influences aren't just theoretical. They could potentially leave their mark on Earth's history.
Precisely. And looking ahead, these external encounters introduce a quantifiable, albeit still small, future risk.
How probable is a, really close stellar encounter in the future?
Well, based on current models of stellar density and movement in our galactic neighborhood, there's about a 5% chance of a star passing within 100 AU of our sun over the next 5 billion years.
100 AU. That's about 100 times the Earth-Sun distance. Still sounds pretty far out.
It is, yeah. It's well outside the main planetary system, but potentially close enough to have a long-term gravitational effect, especially combined with the internal chaos.
Okay, so a 5% chance of a relatively close encounter. And what's the actual risk that this encounter causes something catastrophic for us, for Earth.
Right. So combining that probability with simulations of how such passes affect the planets, the estimated chance of a catastrophic event hitting Earth, things like being ejected from the solar system by Jupiter's influence or colliding with another planet,
Yeah.
due to a passing star within the next 5 billion years is estimated to be about 0.2%.
Okay, 0.2%. That still sounds incredibly low, thankfully.
It is, absolutely. From a human perspective, you definitely don't need to lose any sleep over it tonight. But from a scientific perspective, this 0.2% risk is actually significantly higher than what previous studies had estimated back when they generally didn't account for the long-term influence of passing stars. So it highlights a previously perhaps underestimated vulnerability of our solar system's long-term stability to its galactic environment.
So the isolated clockwork model wasn't just missing the internal complexities. It was also missing the neighborhood effect.
Exactly. And the research can even tell us what kind of passing stars pose the most significant risk.
Oh, not all stellar neighbors are created equal in terms of danger.
No. The most dangerous are, maybe predictably, those that come closest, less than 100 AU, as we said. But, crucially, the risk also depends on their speed relative to the sun.
How so?
Slow-moving stars, those traveling at less than about 10 kilometers per second relative to us, seem to pose a greater threat.
Why slow? Wouldn't fast be more disruptive?
You might think so, but a slower pass means their gravitational tug lasts longer.
Right. More time to exert influence.
Exactly. A slow, relatively close pass gives the passing star's gravity more time to subtly perturb the orbits of the planets. And those small perturbations can then grow over vast timescales, partly because of that inherent chaotic nature of the N-body problem we talked about earlier.
Got it. So it's not just proximity, it's also about kind of lingering influence.
Right, a slow burn disruption, potentially.
And it's not just about a passing star's gravity directly yanking on the planets themselves, is it? I think I read there are other ways a flyby could impact our system.
Yes, that's right. Another widely discussed potential threat involves disturbing the Oort cloud.
That enormous, really distant shell of icy bodies way, way out surrounding the solar system.
Exactly that. A star passing relatively close, maybe even within a few thousand AU, much farther than the 100 AU we discussed for direct planetary effects, could gravitationally stir up the Oort cloud.
Stir it up how?
Basically nudge all those icy bodies, sending a potential shower of comets and asteroids tumbling inwards towards the inner solar system.
Ooh. Like turning on a kind of cosmic sprinkler system aimed right at us.
That's one way to think about it, yeah. Potentially leading to a significant increase in impacts on the planets, including Earth.
Right. And while we mostly talk about stars doing this passing,
right,
other massive objects could have gravitational effects too.
Absolutely. I mean, gravity is gravity. A stellar mass black hole passing at the same distance as a star of equal mass would exert the same gravitational pull, the same orbital disturbance.
Okay, makes sense.
The sources also touch on other, maybe more theoretical risks, things like hypothetical primordial black holes, or even threats from very energetic phenomena like powerful radiation bursts from a passing pulsar or a neutron star. Those could potentially impact us even from light years away, though that's less about orbital mechanics and more about, well, direct energetic threats.
Okay, so let's maybe zoom back out and try to get the big picture here again. We started with this image of a perfectly predictable, isolated clockwork solar system. Nice and neat.
And what the latest research really paints is a much more dynamic, much more complex reality, doesn't it?
It really does.
Our solar system seems to harbor this inherent potential for internal chaos, mainly due to the gravitational ballet of the planets themselves. There's that non-zero, albeit small, chance of serious disruption over billions of years, like Mercury's potential instability we discussed.
And on top of that, it's clearly not isolated. It's constantly moving through a galactic environment, and it's susceptible to these gravitational nudges from passing stars. That adds another layer of uncertainty and, well, risk, both for understanding the past and predicting the far, far future.
It truly highlights how everything in the galaxy is interconnected, doesn't it? Even across immense distances and timescales, distant stellar encounters happening over cosmic periods can have these surprising implications for our own little corner of the universe.
So for you listening right now, What's the big takeaway from all this talk of chaos and passing stars and resonances?
Well, for me, it gives you a much deeper appreciation for the incredibly delicate and perhaps really fortuitous gravitational balance that has kept our home planet in a relatively stable orbit for billions of years now.
Yeah.
The fact that we haven't experienced one of those low probability catastrophic scenarios yet, either from internal dynamics or external stellar passes. It's actually pretty remarkable when you consider the vast time scales involved.
It makes our stable existence feel a little less like, I don't know, destiny and a little more like winning a kind of cosmic lottery.
This deep dive into the surprising chaos and the external influences rattling around in our solar system, it really does make you pause and wonder, doesn't it?
It absolutely does, yeah.
Like, how unique is our solar system's particular architecture? The specific arrangement of our planets, especially the giant ones like Jupiter acting as these gravitational stabilizers, does it represent a really rare configuration? One that allows for the billions of years of relative stability needed for complex life like us to arise and persist?
Especially since it seems we're operating, as you quoted, near the edge of chaos in some ways.
Exactly. And if this kind of long-term dynamic instability and this susceptibility to external stellar influence is actually more common than we used to think, what does that imply for the likelihood of finding other truly stable, long-lived planetary systems out there in the galaxy?
Yeah, and by extension.
And, of course, what does that mean for the potential for stable environments that are conducive to life elsewhere? Is long-term planetary stability maybe a rarer cosmic commodity than we previously imagined?
Definitely something to contemplate the next time you look up at the night sky. Seeing all those distant stars that, over vast periods could theoretically change the very path of the ground beneath your feet makes you think.